Assalamualaikum students. Students, today we are starting with the first lecture of the energetics of A2 chemistry. In energetics, we know that there are two types of reaction, exothermic reaction and endothermic reaction, right? Whether the reaction is exothermic or endothermic, we know that the bonds are breaking and bonds are formed. In the reactants, the bonds are breaking. In the products, the bonds are formed. Now, to be endo or exo, it is decided by what? The bond strengths of the reactants and of the products. If products have stronger bonds, more energy is released. If products have weaker bonds, less energy is released when they are formed. So to explain this whole thing, I'm going to share the screen. But when I'm sharing the screen, you guys are supposed to like and subscribe my channel. Okay. So now coming to this. Okay. These are the notes that these notes are available on my website. That is Chemistry by Zeenat, and the topical past papers are also available over there. And now I am going to share just to explain this whole thing. But during explanation, I'm not going to use these notes directly because I don't want to write on them. And this is not my teaching pattern. Like, I don't write on the notes. I will explain them, but yes, to save time, I will share the notes again and again so that you can see that what you are supposed to write and how I'm going to explain it, okay? And I'm explaining this on a separate page. What is this? Okay. We know that there are two types of reaction. Look, the reactants, they turn into products. You know this. In reactants, the bonds break, and in products, the bonds form. When the bonds break, they need energy. When the bonds form, they release energy. Now, there are two situations. I'm going to copy it. How there are two situations? Look. For instance, more energy is needed and less energy is released. The net enthalpy change is what? The net is what? Endothermic. It's what? Endo. Because the absorbed is more. The needed is more to break the bond and less is released. This shows that when they need more energy, this shows that they have stronger bonds and they release less energy because they have weaker bonds. So in all endothermic, keep in mind, in all endothermic, the reactant have stronger bonds, the product have weaker bonds. So if I draw the energy profile for you people, it would be like this. Look. An energy profile. This is enthalpy. This is reactant. Look. They absorb more. They absorb more. It's not taking prediction, okay. The absorb is more. Look, this is, sorry. I made it for X. It's like this. Look. Reactant to the top. Activation, absorbed energy. Now, absorbed is more, released is less. The enthalpy change is this. Reactant to top, activation. Reactant to product, delta H. Reactant to top, activation. Reactant to product. The arrow is up. delta H positive. In exothermic, you know what is happening? The needed energy is less and the released is more. Overall energy released is more, product have stronger bonds, energy released is more. It is exothermic. It is exothermic. And how you are supposed to draw the profile? Reactant absorb more, released less. Absorb more and absorb less and released. I'm not going to record it again. I will continue this with the same correction. Absorbed is less and released is more. Product have stronger bonds. As a result, the arrow is down, the delta H is negative. Right? So whatever is type of reaction, whether it's exothermic or endothermic, energy is needed, energy is released. If energy needed is more, released is less, endo. If energy needed is less and released is more, X. Right? Now, the next thing is, we have two topics in this chapter. First, we define delta H, formation, bond energy, atomization, delta H, ionization energy, electron affinity, and then delta H lattice, hydration, solution, and their calculation. So your first topic is define the different types of delta H, and second, find delta H. Define and find. You define and then you find. And finding is two types. Are you finding it practically or theoretically? Practically, we use what? Heat is equal to mc delta T. You know, there are more questions on this in AS, P1, P2, P3, and in A2, in P5, it is used more than P4. There are more questions on heat is equal to mc delta T in P5, right? In the ATP kind of situation, right? No, it's not ATP. We call this evaluation and designing, right? Now, heat is equal to mc delta T. We are going to do it, right? But that is the like primarily for P5. And theoretically, we will use Born-Haber cycle as well as Hess. So the first thing that we are going to do is what? Define. And which definition you are going to do at the first? Enthalpy change of formation. Let me, okay, done. Enthalpy change of formation. You know what is enthalpy change of formation? Standard enthalpy change of formation. Standard enthalpy change of formation. Enthalpy change of formation is enthalpy change when 1 mole of a substance. Look. Enthalpy change measured under standard condition when 1 mole substance is formed from its elements in standard states. Enthalpy change measured under standard conditions when 1 mole substance is formed from its element in standard states under standard condition. You're making 1 mole of the compound 1 mole of any substance from its elements. See, for example, you are making 1 mole carbon dioxide gas from its elements. What are the elements? Carbon and oxygen. The carbon is solid, the oxygen is gas. In carbon dioxide, the bonds are formed. In carbon and in oxygen, the bonds are breaking, right? Carbon solid is graphite. You must know that in energetics, when we use carbon, this carbon is not diamond, this is graphite. Graphite is the most stable allotrope of the carbon, right? So in the graphite, the bonds are breaking. In oxygen, the bonds are breaking and new bonds are formed. If the bond broken, they need more energy and less is released. Endothermic, but if more stronger bonds are formed and weaker bonds are broken, automatically more energy would be released. So enthalpy change of formation could be exo and could be endo, depending on the bond strength of the reactant and product. Enthalpy change of formation of 1 mole of sodium chloride from its element. What are the elements of sodium chloride? Oh, sorry, it's solid. From its elements, sodium solid, it is a metal, and chlorine is what? Gas. Enthalpy change of formation of H2SO4, liquid, from hydrogen gas, from sulfur solid, from oxygen gas. You are making 1 mole of calcium hydroxide. From its elements, what are the elements? Calcium solid, hydrogen gas, and oxygen gas. Like you are breaking the bonds, you are breaking the bonds, you are breaking the bond, and the bonds are formed, right? During bond breaking and making, whatever is enthalpy change is called enthalpy change of formation. But element and the thing that is formed. Now, if you are making phosphate ion from its element is phosphorus solid, oxygen gas, and it's gaining how many electrons? 3. Perfect. You are making phosphate from its element. You are making magnesium ion from its element, magnesium. And it's not going to gain electron, it's losing 2 electron. You can write the 2 electron this side and you can write it on this side. It's perfect, right? So you are making 1 mole of anything from its element. That is called what? Enthalpy change of formation. It could be exo, it could be endo. After formation, your next topic is what? Bond energy. You know what is bond energy? You know what is bond energy? I want to show you the notes. Look. There are 2 types of reaction, exothermic and endothermic, and then define and finding, and then enthalpy change of formation. I'm not going to waste time in explaining this. You know this. You can rewind, you can watch it again and again, and you can watch this at any speed. It's up to you. Okay. जितनी दफा देखना है देखो बेटा. तो ये मैंने एक्सप्लेन कर दिया आपको. अब मैं बॉडी एनर्जी एक्सप्लेन कर रही. Right? I'm at bond energy. And you know what is bond energy? Bond energy is the amount of energy needed to break what? It's the amount of energy needed to break 1 mole of the bonds, covalent bonds, in gaseous substance. You know why? In all the gases, we consider the gases to be what? Ideal. Ideal. If they're ideal gases, they don't have intermolecular forces. They have only what? Covalent bond. Because if something is gas, right? Like we are not talking about ionic, we are not talking about the other things. Ionic are just ions. We are talking about simple molecules. We are talking about even like when you are breaking covalent bond, that's the energy to break covalent bond, right? Bond energy is the measure of the strength of covalent bond. Higher bond energy, more stronger is the covalent bond. So in gases, we say that there is no intermolecular force, there is no like assuming or even practically they are negligible. So it's the strength of the covalent bond. So if you're providing heat to a gaseous molecule, you are actually breaking the covalent bond, right? So it's the amount of energy needed to break 1 mole covalent bond in a gaseous substance. So wait. If it is energy needed to break covalent bond in a gaseous substance, for instance, I have bromine liquid. Now you know that in bromine liquid, there is covalent plus what? IDID. Now when you will provide heat or any form of energy, this energy will break which bond first? Weaker. A simple rule. A simple rule. When bonds are formed, which bond will form first? The stronger. Like if there are choices to many bonds to be formed, the bond that is formed first is the stronger one. And which bond will break first? The one which is weaker. So is the covalent weaker or IDID? Definitely IDID. So which one is going to break? IDID. When the IDID break, it is vaporization. The bromine will change from liquid to gas, and now only covalent is left. Now, if you provide energy, the covalent break, and that is called what? Bond energy. Bromine atoms are formed, right? Now, suppose you have water, just take water. In H2O liquid, there is covalent plus hydrogen bond. Now, if you are providing energy, do you think covalent will break? No. It's what that is going to break? Hydrogen bond. When the hydrogen bond break, the water will turn from liquid to what? Gas. Okay, when I teach in the classes, sometimes I find that some students think that hydrogen bond is very stronger. I agree, hydrogen bond is stronger among intermolecular forces. Like hydrogen bond is stronger than PD and IDID. But hydrogen bond is weaker bond. It's intermolecular forces. अगर हाइड्रोजन बॉन्ड तोड़ना इतना आसान होता तो कोवेलेंट बॉन्ड तोड़ना इतना आसान होता तो कोविड टाइम्स में लोग पानी उबालते, ऑक्सीजन बनता, सिलेंडर भरते, इशू ही ना होता, सिलेंडर इशू यानी इट वाज डिफिकल्ट क्योंकि by boiling water you don't get oxygen, you can't break the covalent bond. When you are boiling water, it breaks the hydrogen bond, it breaks the intermolecular forces, the molecule get further apart, the molecules are not breaking, the molecules are getting far, they turn into steam. It's vaporization. It's what? Vaporization. Enthalpy change of vaporization. After vaporization, what is left? Covalent. Now, can you tell me in 1 mole of water, you know I'm using 1 mole. I'm not using 1 molecule. In 1 molecule, 2 bonds. In 1 mole molecule, 2 mole bonds. Look, in 1 molecule, 2 bonds. In 1 mole molecules, 2 mole bonds, right? Like 2 moles. 1 mole need 1 bond energy, kilojoule per mole of the bond. Kilojoule per mole of bond. Amount of energy to break 1 mole of the bond in a gaseous substance. Another bond energy. So actually 2 bond energies. 2 times bond energy, making 2 hydrogen atom and oxygen atom, right? They are gaseous, definitely. I think you get the concept of the, like, if it is chlorine, okay, if it is chlorine, there is no intermolecular forces, kind of negligible intermolecular forces. It's already gas. You are just breaking the covalent. When you are breaking the covalent, you get what? 2 chlorine atom, and this is what? Bond energy. Okay, now delta H atomization, and at the end, after atomization, we are going to link bond energy and atomization, right? Delta H atomization, पता है क्या होता है? Enthalpy change, energy needed when 1 mole atoms are made from its element in standard state. Look, you are making atom from its element. When you make compound from its element, it's called what? Formation. When you make atom from its element, atomization. You make, when you make compound, it's called what? Formation. When you make atom, it's called what? Atomization, right? So you are making atom from its element. You are breaking the bond of the element. The element turn into atom. Now elements are of 2 types. They could be metal, they could be non-metal. They could be what? Non-metal could be solid, could be liquid, could be gas, depending on the strength of intermolecular forces. Now, metal. In metal, the metallic bond break. The metallic bond break. The metallic bond break, right? Now, you are making 1 mole of, wait, this way. Yeah, again and again. When I teach to the students in the class, most of the time I used to say, look at the board, come to the board. But you know, right now I am teaching all alone in the class. All alone in the room, you can say, okay? So sometimes I even say, shut up. Like, these are light moments which we enjoy in the class, and right now there is no one. Okay, I hope you are enjoying. So you are making 1 mole. I will talk like this, okay? I'm in the imagination that you people are listening, right? Like some imagination. Okay, 1 mole atom, 1 mole copper atom from copper solid, 1 mole of sodium atom from sodium solid. Which bond is breaking? Metallic. 1 mole of magnesium. Magnesium. So you are breaking metallic bond and you are making atom. Understand? Now coming to the non-metal. Now you are making 1 mole of nitrogen atom from its elemental state, hydrogen gas. 1 mole of hydrogen atom from hydrogen gas. 1 mole of chlorine atom. Chlorine gas. I'm deliberately doing for gas. And now liquid, some liquid, like what? 1 mole of bromine atom from bromine liquid, elemental state. 1 mole of iodine from iodine solid. So you are actually you are actually making 1 mole of atom from its element. The elemental state is gaseous, gaseous, gaseous. In gases, the intermolecular forces, the ID are negligible. Because there would be ID only because they are same atoms, no electronegativity difference. There is only ID. And the ID are negligible, therefore they are gases. So covalent bond are breaking. In these gases, covalent are breaking. But if we come to bromine, iodine, it's not just covalent, right? It is covalent plus ID. In these, covalent breaking. And in these, covalent plus ID, London forces are breaking. Now listen, another thing. For 1 mole of atom, if suppose the enthalpy change is plus 100, for 2 moles, it will be how much? 200, 300, depending on the number of the moles. But it's kilojoule per mole. Per mole of what? Per mole of what? Of the atoms that is formed from its element. Now, I'm going to link the bond energy and the delta H atomization. Suppose I'm making 2 moles of chlorine. Look, I'm making 2 mole of chlorine atom from its element. Is it 2 mole of atoms? Is it 2 times atomization? Yes, because it is made from its element. And if I break the covalent bond energy in gaseous, so do you think that the bond energy of this is equal to 2 atomization? Yes. It is bond energy equal to 2 atomization. Now next. 2 nitrogen from N2. Again, can we say the bond energy is equal to 2 atomization? Yes. So 2 atomization is 1 bond energy. 1 atomization is half bond energy. 1 atomization is half bond energy. But if I apply this on bromine, for instance, you are making 2 mole bromine atom from its element. It's bromine from its element, which is liquid. It's not bond energy directly because it is a liquid, but it is 2 atomization, yes. It is 2 atomization. Now, if I break the ID, the bromine liquid will turn into bromine gas. The ID break. The ID break. So is this delta H vaporization? Yes. And now the covalent bond break and it turns into what? Atoms. Covalent break. When the covalent break, it's what? Bond energy. Can we say that from bromine liquid to atoms, we can go this way and we can go this way? Is it a Hess cycle? Yes, of course. It's already there in a paper in, I think, 2022, if I'm not wrong, 2022 June or November. Like, this is a question of 3 marks, the whole Born-Haber cycle construction and the calculation of, I don't remember that they've asked in that paper to calculate the vaporization or something like this, but you were supposed to draw this cycle. And now look, is this just one route? One route is this. And what is the other route? Look, it's this. There are 2 routes. So can I say that 2 atomization is equal to delta H vaporization plus bond energy? right? Now, if I want to show you the notes, it's bond energy, full explanation, then atomization for metal, for non-metal, and then if element is liquid or solid, this is vaporization, bond energy, this is sublimation, bond energy, and the next topic is what? Ionization energy. That I'm going to explain in my next lecture. In my next lecture, I'm going to cover 3 topics. One is ionization energy, one is electron affinity, and one is delta H lattice, right? Students, these notes are available on my website, right? Go and get it from there. And even you will get the topical paper, past papers over there. You can even, if you want to join my live classes, you can contact me. All the information are on my website, right? अब तक के लिए इतना काफ़ी है. अल्लाह हाफ़िज़.